Alright. So for this integral, sorry, I have feedback from my own voice, which is distracting. Okay. For the Gaussian quadrature, there was a problem with the roots. The roots were not accurate. I think I know why, but we know that they are accurate enough to get a certain precision if we don't use too many points. So a value of n which is relatively small, everything's going to be fine. And because of that, I want to start working on a physical example, which is directly from a course in computational physics given at the University of Ottawa. Something like 2 or 3 years ago, don't remember. And it's a treatment of molecular vibration. So imagine you have 2 atoms in a molecule. They have a certain distance at which they like to be, because if they get closer they repel, and if they go farther apart they attract. But if you give them a certain energy, they will vibrate like this, because even though they are at the bottom of a potential well, they have a little bit of kinetic energy which allows them to go up and oscillate like this in the potential, in the energy curve. So the question is, can we compute this vibrational behavior? To do this problem, which really we're talking about atoms, so you could expect that we would need quantum mechanics to solve the problem properly. But in this case we're going to use a semi-classical approximation. I'm just going to read you a little bit about the problem so that get a bit of context. I'm going to show you the assignment. So that you see visually what I'm talking about. Okay. Consider a diatomic molecule. Atomic nuclei are more massive than electrons by a lot. Roughly 1,000 times, but big more, at least 1,000 times, usually more. The latter adjusts, so the latter being electrons, adjust their position instantaneously with the position of the nuclei. This is the Born-Oppenheimer approximation. The potential energy between the atoms is therefore parametrized by the distance between the nuclei r. So we don't care about the electron clouds, we care about the distance between the nuclei. A potential, which is often used in practice to describe how the energy varies with different choices of distance between the nuclei, is the Lennard-Jones potential. And we see, okay, we don't see it here, so I'll just write it. Okay, Lennard-Jones potential. It's V of R equals to 4 times V0 times A over R to the 12 minus A over R to the 6. Okay, and I forgot the equal sign there. Okay. So V0 is the dissociation energy, the amount of kinetic energy you need for the molecules to be able to be stretched to infinity, so to no longer be coupled. And A is an empirical constant. It's kind of a length scale, whereas V0 is kind of a height scale, you know. VR has a minimum at 2 times 1 over 2 to the 1/6 times A. Okay, so 2 to the 1/6 times A. If you put that here, you get a minimum. Around this minimum, the nuclei may oscillate. The goal of this exercise is to study the vibrational energy levels of the nuclei. In principle, these energy levels, En, are given by Schrödinger's equation. So if you've seen Schrödinger's equation, you know what it is. If you haven't seen it, I doubt that this would be helpful. Basically, Schrödinger's equation is the dynamical equation of quantum mechanics. And perhaps you can or cannot see this, but this is a picture of the Lennard-Jones potential. As you may or may not be able to see, this is R equals to 0, and the high energy here means repulsion at short distances, and here it means attraction at large distances. And here is the minimum, and the oscillation will be here. Okay. So just to be clear, for this semi-classical approximation we're going to use, you're not expected to get why we have the formulas that we have. Okay, it's pretty difficult. It's not even an introductory course in quantum mechanics. It's more advanced undergraduate course in quantum mechanics. It's called the WKB approximation, and it is justified by the relatively large masses of the nuclei. Okay. So basically, as in this picture, if you have a certain amount of kinetic energy, you will be able to oscillate. Okay, say you have this much kinetic energy, you will be able to oscillate between this point and that point. Okay. Why? Actually, right. Never mind the. Just roughly speaking, okay. If you have no kinetic energy, you will be confined to the bottom of the potential energy well. If you have a little bit of kinetic energy, you will be able to move a little bit, and the height that you can move will depend on the amount of kinetic energy you have. If you have V0 kinetic energy, then you're able to go up to here, and you're also able to go up to here, but in that way the curve never touches the x-axis, which means that you're able to escape to infinity, which corresponds to the molecules being completely dissociated. Right. Because now the kinetic energy can compensate for the potential energy. So if you start here if you start at the bottom with a certain amount of kinetic energy equal to this, you can exchange your kinetic energy for potential energy and move up to here. So kinetic energy restrains your motion, and if the energy is between minus if the total energy is between minus V0 and 0, the motion is restricted between the turning points RA and RB, for which the momentum is 0. So if you climb at that point where you have to come back, you have 0 kinetic energy, which means you have 0 momentum. And so, because you have an equation for the total energy as the kinetic plus potential, if you say potential equals to 0, it means that total energy equals if kinetic equals to 0, total equals to potential. So if you fix the total energy and you need to find the value of the spacing between the two atoms for which the potential energy is equal to that fixed value, you're basically solving a root finding problem. Okay. So you're confined between these 2 points, and the way you do it is you define the action as the integral over a closed closed cycle. Okay, quantum mechanical stuff of the momentum. So this is the momentum if you include the square root of 2